get to do practical stuff. So hi, we're talking about light, second part, and we'll talk about specifically how we can analyze light, and if all is well, you all got a little, one of these slides. Yes, Drew and I still call them slides because they seem to be sitting in the projector. They're slides, this is what they are. But there's a little, what's called a grism in there, and so this is actually your own personal spectrograph, and we will use that when I do the demonstration. So first we're going to talk about what the second kind of light is, and then we'll do a demonstration which will completely fail to be recorded by my iPad, so if you're trying to look this back later, there's nothing for you to look at, right? So this is the part where being in class is good. We'll talk about the different kinds of spectra that we can have, and we'll talk about Doppler shift, right? So these are the concepts that we're going to use throughout learning about the universe, because this is how we learned about what stars are made of and how fast they were going. All right, just to remember, I always want you to have your voting card ready to roll, because we're going to have a question sort of like 3 or 4 slides in. So again, slides on the projector. So which one of these stars is hot and dim? So which one is hot and dim? Let's see. Putting in 1, 2, 3. Yes, okay, we did that last time. Which one was cool and dim? 1, 2, 3. Great. We all got this from last Tuesday. Why does the temperature increase from the left, right? So I know this is a stone cold old meme. I don't care. I'm old. My memes are old. But why does it change like that? It is because in about 100 years ago, as you can see from this lady's absolutely spiffing, almost 19th century dress and hair, Annie Joan Cannon classified stars for a living, right? This was part of her job as a computer at the Harvard Observatory. And so women at that time could not initially be faculty, of course, because reasons. But they were hired if they could do math well, so they were literally the computers of the time. And one of the things that they were doing was they were getting spectra, they were getting observations of stars. They came in as photographic plates, and they classified them in a nice warm room. So this was ladylike work. And so what she came up with was that, some stars on the blue on the right side and the red on the blue on the left side and red on the right side. So if you classify from blue to red, you're essentially taking temperature going the other way. That's how it got started. She literally just went from blue to red. If she had started from red to blue, the temperature range would have been from left to right. So that's why we are stuck with it, because that was the initial classification that she made of the various colors of stars, realized that there was structure in that, realized that there was a pattern, and so this became later the Hertzsprung-Russell diagram is completely based on her work classifying stars. So we already did the black bodies. Sorry, that was still available. So we talked about thermal radiation. Basically, if I heat it up, it starts to glow. And now we'll talk about the second one as well, electron transition. So if you're in a so hopefully you've seen the video, but sort of screen grab this here. You've got the nucleus and you've got electrons sort of floating around, right? The simplest model that you sort of see has them sort of orbiting. They're not really orbiting, but that's sort of the easiest thing to keep in mind. And so you have like one proton here and one electron. That's the absolute simplest atom that you can have. Is this familiar to you all? Did you all encounter this at some point in high school? Okay, fantastic. We're going to take that a little step further, which is, actually I only saw 2 people nod and everybody else just looked straight ahead. Hopefully he doesn't notice me. You all are okay with this point, right? Okay, fantastic. You're going to say yes, because then I can keep going. So for hydrogen, we have one nucleus, that's the proton, and then an electron floating around it. And what physicists noticed in the beginning of the 20th century is that electrons were only allowed as particular steps. And so like stepping up on a step, I can either take a full step up, but I can't take a half step up. I stumble, right? So electrons are allowed at very particular levels. And the further away they are from the nucleus, if they step back down, they give off photons. So in order to bump them up, you need to give them some energy. So that's discrete. That's the quantum in quantum mechanics. That realization that electrons are only allowed in particular discrete steps was the part that introduced quantum to quantum mechanics. And so if you have that, if you go from one step to like a step up, there's a little gap of energy, so you have to give the whole thing a little bit of energy, either by bumping it or by giving it light at exactly the right frequency, right? So this transition is one particular kind of energy level. So it only allows, if you give it exactly that frequency, then you can bump it up, or if it bumps down, it gives a light of exactly that frequency and wavelength. And so what we then realize that there's a whole series of those where you go like, this is the ground state, this is where it has no extra energy. You bump it up to 2 or 3 or 4 steps, you have a very particular kind of energy. If it drops back down, you get a very particular kind of light. And so these are the only steps in the hydrogen atom that are allowed. But hydrogen is the most common element that we have, so this is going to show up. And so if I take hydrogen and I take those steps and I let the electron fall back down, I get light at a very particular wavelength. So wavelength on the x-axis here, and so you only get light at those particular wavelengths. Now if I put a big cloud of hydrogen behind, and I put a light source behind it, it will only absorb at those particular kind of wavelengths. So that is a fingerprint of hydrogen. If I see this pattern, 1, 2, and then space, and then here, and then over here, so at between the 600 and 700 nanometers, there's a red line. Between 500 and 400, there's 3 lines, right? So I can actually see there's a pattern to these lines, because those are the allowed steps for the electron if it only is surrounding one proton, if it's in a hydrogen atom. With me so far? Okay, so we can fingerprint hydrogen. This is the fingerprint of hydrogen if I'm seeing this emission, or I'm seeing those absorption features happen. So if I have a cloud of hot hydrogen, I'm seeing these lines, right? I'm over here. This is how astronomers put the observer somewhere. They just put a giant eyeball on the whole graph. It's like, this is where we are, this is where we're looking at it. So if we're looking at it and it's just hot hydrogen gas, then it's giving off, then occasionally the electron will bump back down and it will give off light at one of these particular wavelengths, right? So it drops from the 3rd step to the ground step, it gives off that one. So if I put a sun or a star behind it and I get a lot of light coming through the high cloud of hydrogen, then at that particular wavelength, that's where the electrons actually swallow a little bit of the energy to that particular wavelength and actually bump up. And if they then fall down, they sort of like drop back down. They emit the light in every direction. So not all the light makes it directly to us, right? It basically gets absorbed and then re-radiated in a different direction. So if there's a bright source behind and there's a cloud in front, you start, and you want to know what that cloud is made of, what that atmosphere is made of, you start seeing absorption features. Okay? So these are the 2 things that can happen. And so you really have 3 kinds of things in the sky. You can either have a hot source that has a particular temperature, and so you see it radiate everywhere. That's the black body, right? So if I have a giant ball of hydrogen, or a giant ball of gas, a star, it will radiate at all wavelengths, and that just depends on the temperature, where the peak is. If I then say, like, I have a cloud of gas in space, and that is hot for some reason, because it just got ejected or something, or just been bumped, so there is energy in there, and if the electrons drop back down, I get emission at very particular wavelengths. If I put the cloud of gas in front of a hot source, I basically have light everywhere except where that cloud of gas has been taking the energy from the light and re-radiating it in every direction except only a small part in my direction, so I don't see the light there is missing. Okay, so I've got these three scenarios, and the neat thing is that if I see emission lines or absorption lines, I can look for fingerprints. So I can do, astronomy CSI, CSI astronomy, currently not one of the family being played, but I'm sure it's just a matter of time. And so the physical situation what makes this spectrum, I have a question for you. I have a spectrum that has light everywhere except for these few absorption lines. So is that A, there's a bright star, there's a cloud, and then there's me. B, there's a cloud, there's a bright star, there's me. Us the observer, here there's a star, the light goes straight to the observer, or there's a cloud of gas and goes straight to the observer. Voting in 1, voting in 2. Let's see. Yep, we're all in agreement, right? There's a cloud in between that's absorbing, that's made out of something and that is absorbing. You see the fingerprint as absorption features. All right, if I just see the visible spectrum, which one of these can it be? Is it voting in 1, 2, and 3? What's the most likely one? Everybody agrees that that's just the C, the star. If I'm seeing emission lines, which one of these is it? 1, 2, and 3. Fantastic. All right, these are the questions that. Oh, and I see this happen. What's happening here? All right, let's hear your opinion. Voting 1, 2, and 3. I see a lot of B here. Interesting. A mix of answers. So I'm going to walk around, turn to your neighbor, and even if the two of you agree, explain your answer to them and convince them why you're right. You have 90 seconds. Vote again. Voting 1, 2, 3. Oh, you definitely convinced each other. Got A, B, and D. All right. Here's a trick. It says iron there. This was hydrogen. Hydrogen is simple. It only has a few steps. Iron has a whole massive steps. So you see all these different emission lines. It has all these different transitions. So it almost looks like it's completely filled up here, but that's all different little transitions within iron. Iron has, oh, do I remember? No, I don't. So it has a much bigger nucleus, and so it has many more electrons, and all those electrons have different steps to sort of step up and down. So if we're seeing this pattern, loads in the blue and ultraviolet, a bunch of the green, and a few red lines here, then we know it's iron. So we can fingerprint iron that way. And so hydrogen, nitrogen, oxygen, iron, they all have different patterns of steps of the electrons are allowed to be in, and so they all have slightly different or massively different patterns of these emission lines. So if you want, I said CSI for a reason, if you hear them go, oh, figure out what this is made of, right? What you actually do is you take the material that you found, you evaporate it, you basically make it really energetic, and then look at the spectrum and see which elements are in there. So you can look at elements like you can look at a star, you can look at spectra from a distant star and say, oh, it's got these elements in there because they match the pattern that I see in my laboratory if I just, I don't know, evaporate a bunch of iron. That's literally just, I let the pan sit on the stove for a little too long, you're starting to evaporate iron. So that's going to be in there, and you can see for that, you can look at that pattern. You can do the same thing for well, oxygen is in the air, nitrogen is in the air, and hydrogen, well, you'll have to let some out of the balloon or something. But you can fingerprint each element that way. And the neat part is, if you see these really pretty Hubble pictures, we basically color code by like looking for this particular line. So red here is that line over there. So we color code the elements that we're looking at. So blue, for example, is the line that we know comes from hydrogen. So blue is the hydrogen, red is the oxygen, I think, and then I think green is the iron. And in that way, we can sort of look for very particular elements in planetary nebulae. Or, for example, the sun, right? So the sun has an atmosphere, so it has a hot surface and then a cloud of stuff around it. So the cloud is absorbing, the atmosphere is absorbing. And look at all the different patterns that are in there. It isn't just hydrogen. The sun is made out of mostly hydrogen. That was another one of the Harvard computers' results. But the other part is that it has all these other elements in it. So funny enough, and since we just had the eclipse, at least in my mind, we just had the eclipse, you can either look at the sun, a hot surface, and there's this cloud around it, so some of the light disappears because it gets absorbed by this atmosphere, the corona, and then re-radiated in every direction, so not enough goes to your eye, so that you get these absorption features. Or, in the case of an eclipse, you don't see the surface of the sun, you just see that scatter come, like whatever's coming out of the corona, so you just see the emission lines. So during an eclipse, you take a spectrum of the sun during an eclipse, you can actually see what the atmosphere is made of, and that's what they did back in the 19th century. Two people did this at the same time, and they found this, this is a spectrum that was taken later, so you can sort of see the arcs. So this is the same picture of the atmosphere of the sun, and there's hydrogen, there's magnesium, Na, that's natrium, so sodium. I have to translate that in my head because in English it's sodium, and everybody on the continent calls it natrium, which sounds more Latin. But anyway, so that's what Na comes from, and then so hydrogen, more hydrogen, and hey, what's this here, right? There was suddenly an extra line, and that was an unknown element up until then, and so named it after the sun, called it helium. Funny enough, helium is the second most common element in the universe, and we only found out about it in the 19th century. And the reason for that is that if you release helium here on Earth, and all of you have done this because all of you have been given a small balloon for your birthday, and then you let it go and watch the balloon disappear into the sky, didn't you? At least my son definitely had that experience. Does anybody remember losing their balloon and just watching it float off into the distance? Right? That's what helium does. So helium not only goes up into the upper atmosphere, it actually leaves the atmosphere completely. And so our planet doesn't have a ton of helium. Helium is literally a byproduct of natural gas production that's coming out of the ground. And so we have a limited amount of helium here on Earth. But the sun, being much more massive, can actually retain its helium just fine. And so in its atmosphere is lots of helium. All right, so now we get to the fun part. You go like, all right, enough talking, more showing. And so we'll get to the, I'll make sure that we get good and dark here.
And this is the time where this experiment will not work if you have anything in front of you.
Yeah.
Phone, laptop, little LED flashlight. I just turned the projector.
Yes, that would help. All right, so we're going to start with just a hot source, right? So what I've done here is I'm putting some electricity through this wire here, and so it starts to glow. I'm giving this a temperature. So if you look at this with your, you may have to angle it a little bit. You look at it, and then you may have to look a little off to the side, right? So then you see, does everybody see the rainbow? Yeah, have you got the rainbow? You notice that there's also a little bit of a horizontal black stripe? And that's because I think, here we go. There was a little thing in the way that had nothing to do with spectroscopy. Okay, it's still actually holding, it's holding like this, those two black stripes that you see, horizontal black stripes. There's no gas or anything, it's just holding the filament. And so that gives off light across the spectrum. You see the whole rainbow here. Now, all right, okay. Start by switching it on, not electrocuting each other. All right, who can see the rainbow? Do you see a rainbow? Or do you see really bright lines and some dark bits in between? Yeah, I will say that I have extremely bad night vision, so I'm basically talking to a completely empty room as far as I can tell. So if you please say yes loudly. And so this is hydrogen, right? We have a tube full of hydrogen that we're basically sending a current through so that all the hydrogen electrons get excited, bump up to a higher state, fall back down, and so we're seeing the light that's coming off this. So this is a way to actually make a lamp. So this is hydrogen.
Next list.
Now it's like, here we go. And is this a different set of lines? Yeah. You see the big bright yellow line, for example? So this is helium, right? Okay, so we have helium on this side, and Drew has better night vision than I do. He ate his carrots. So you can already, like, you can fingerprint, you can tell that there's a very clear difference between hydrogen in one case and helium in the other. So if you see a cloud of gas and it's just made of one element, you can say, okay, it's this or this. See a mix of the two, you'd see both types of lines. So let's see, what do we got here now? Argo.
This is how one of my lasers works, the one that makes blue and green.
All right, switching it off. Okay, switching to the other lamp. So your eye might just see pink as a color, right? So
But you see 2 or 3 green and blue lines and a violet line, weak red and yellow. Argon gas makes green lasers.
do you, depends a little bit if you see green on the left or the right, depending on how you hold your slide. But, so argon is another, so helium, argon, and helium and argon are noble elements, right? So they don't react to anything. So you just see those. You don't see them attached to anything. Hydrogen, on the other hand, is attached to carbon, oxygen, what have you, right? So that's usually in some sort of combination, but it also appears completely on its own in space. So there were in the 19th century, everybody was sort of working on their own. It was not a great way to do science. You always do need to do science together, especially talking to each other. So in Germany, there was somebody trying to figure out, like, he made all these lights with, and he would burn various elements and then look at the resulting spectra, and so take photographs of that and carefully measure all these lines, where they would appear. And in the meantime, you had astronomers looking at stars, noticing that there's all these dark little stripes in there. So the computers at Harvard finding all these neat little lines where the absorption was happening.
That one will be a little brighter.
Yeah, there we go. So, this is always a very exciting class for me and Drew, because will we actually wipe out on the tables, or will we actually electrocute ourselves? So far, so good, but you know, it's a little. All right. Wow, this looks different, and yet a little familiar. Has anyone seen this particular color before? Maybe at night while driving. I'm standing in front of the mic.
Or the sign at your favorite bar.
Or diner. My diner has these. So, it's neon. Neon signs, neon lights. The bright neon lights, right? So this is neon. This is so filled with neon, and really, it's the only reason that neon works so well is because you've got all those lines all over the place, so you just have to put colored glass over it to get a slightly different color. But this is was used. So was it cadmium or neon? neon lights is for, you know, the neon lighting, and you have the other orange lights that work for street lights. Sodium,
Yeah,
thank you.
I'm gonna show mercury, then we'll show sodium.
Yeah, so we'll get to that. Okay. Mercury, so this is definitely the tube not to break. Hot vaporized mercury is not my favorite thing to breathe in, so,
So that's the color of most street lights, and astronomers hate it because it's a very white, bright light.
this is,
It's harder to filter out of your telescopes when you're doing astrophotography.
so.
Now there's high pressure sodium and low pressure sodium, and you can put a filter on your telescope and it makes it disappear. So street lights are going to kind of an orangish, almost brownish tint. Well, I take that back. Now they're turning blue again because they're putting LEDs in the street lights. Fortunately, LEDs normally shine down, which we like that in street lights. It's called full cutoff. If it's shining down, it's not up there like these street lights used to be.
So funny enough, I think in West Berlin and in East Berlin, they had made some different decisions regarding, different governments. So different decisions regarding like what kind of street lighting are we using. So I'm fairly certain that West Berlin has bluisher light, more bluish light, and East Berlin still has cadmium lighting for the street lights.
I do not have the sodium here.
Oh, sorry, sodium, and sodium is currently missing, so, okay.
But sodium, you've seen sodium street lights. They look orange, weird brownish yellow.
I think most municipalities are trying to get rid of them, because basically LED
Yeah,
lights.
they're all going to LEDs.
LED lights, sorry, I did a hand gesture that nobody saw. So, these were the lights that were fairly efficient, and as a municipality, you're trying to, if you have to light streets, you're trying to come up with like an efficient light that doesn't break down, so you have to send a crew out to repair it. And that's what these things did, but LEDs last 10 times longer and take 10 times less of the energy, so that's an easy budget decision to make. Ooh, which one do we have here?
There's a different one, and if you see that, it might be an extrasolar planet we could live on. Oxygen.
Here we go. So we see oxygen, and we see hydrogen, for example, and we see oxygen, hydrogen, carbon dioxide. All of these have different line patterns. So if you see a combination of the different patterns in exoplanet, in a different planet than our own, of course we would be super interested in those because that might herald life, or at least could be a biomarker. This is a whole discussion. This is literally a whole field of, just in case it explodes.
Another weird one.
But if we're looking for like, if you see oxygen and it hasn't bound to something, right? Oxygen, if left alone, will either, on a metal planet, for example, will rust the planet, then you get Mars. If you leave oxygen alone with lots of carbon lying around, then you, well, essentially get Earth, but we also see free oxygen floating around and free carbon, methane, for example, carbon gas. If so oxygen and carbon dioxide are both in the atmosphere, then something is keeping the balance. That something that could be volcanoes, that something could be lots of plant life. So that's a thing that we're looking for in planets other than our own. And we're getting to a point that our instrumentation gets so good. I just spent a week hearing about plans that we have for the Habitable World Observatory. It will look at exoplanets, at planets the same size and mass as our Earth, and look for these lines. It will look exactly like that. It will look for those lines. Does it have oxygen? Does it have carbon dioxide? Does it have water? Does it have maybe free-floating carbons of methane and stuff? Does it have life on it? Because the life might not be able to talk. It might just be a whole bunch of pond scum or forests or what have you, but it will leave a fingerprint.
That one's gonna look similar. First one you saw was oxygen. This is two oxygens and hydrogen. This is water. We definitely want to see that if we look out far, far away to another planet.
So we look for the combination of lines, and you see that there's loads of them, right? And so some of them give a good signal in blue, other in green. Some of them you have to go to the ultraviolet for, and so that.
Pretty.
So we'll look at a star and we'll try to find the absorption lines made by as the planet goes in front of it, right? As the planet goes in front of it, a little bit of its atmosphere has starlight shining through it, and we can look for the composition. We'll talk about this more in depth when we talk about exoplanets. I'll spend a whole week on them, but this is the exciting thing that we're hoping to find. We're hoping to find the signs of life, not just the hot thing that they're orbiting. All right, did everybody actually see the pattern of lights? Excellent. All right, so well done. You did your first spectroscopy. It wasn't that hard.
Chairs are at both the back doors. Please return the expensive diffraction grating slides.
Yes, we only have a limited number of them. So, okay, I think the lights are coming to get back up. These are LED lights, so, which is nice because I don't burn my stuff on the cove lights anymore. But yeah, so this is how we can fingerprint different elements. Now notice that you weren't moving with respect to these lamps, right? So they weren't your neighbors saw them at the exact same spot as you did. Now the neat part is, I need to switch off the thing. Is that we can look for these things to be shifted, right? It's a particular pattern. That pattern still looks the same if it shifts through the red or it shifts through the blue. Now, you are familiar with the Doppler effect. You might not have heard that that's the Doppler effect, but you have heard the Doppler effect because you've heard the LMPD or the fire brigade or somebody go by. You heard the siren go up in pitch as it went towards you, and as it went by, you go down in pitch. You've heard that bit. Like, you actually use this unconsciously. Oh, the car is coming towards me. Oh, the ambulance is moving away from me. You can hear that already, and that effect, like the frequency changes as it moves with respect to me. That is called the Doppler shift. So if I'm seeing the same pattern, but everything has moved towards the red, I'm calling that redshifting. If I'm seeing the same pattern as moving towards the blue, I call that blue shifting. And so the laboratory spectrum, that's at rest. So this is our laboratory. You were at rest with respect to that, right? You weren't moving towards it, you weren't moving away from it, so you saw the lines at the exact same, always at the exact same spot. But if you were, say, running towards, please don't do that, running towards the laboratory, you would see everything blue shifted. And if you were running away from it, looking over your shoulder, looking at the spectrum, you see everything red shifted. Or maybe easier, I load this whole thing up on a car and drive really, really fast because then you see the effect. So here it's blue shifted, it's the same spectrum. So if it's stationary, I see the same pitch whether or not I'm sitting at the back or the front. But if it's moving towards me, I scrunch the wavelength so they become bluer. And if I look at a horn moving away from me, the wavelength becomes longer, so I hear a lower pitch, I hear a lower wavelength. So this observer, if I see something moving towards this observer, like this is the direction of motion, this observer sees blue shift, this observer sees red shift. You should see what my spell checker makes out of red shift a lot of the time. Anyway, so we can tell whether or not if it goes towards blue, shorter wavelength, we see blue shift. If it goes to longer wavelength, we see red shift. Really want to emphasize that because this is our second tool, right? So with spectroscopy, we can fingerprint what the thing is made of. We can literally get, it's got this much hydrogen, this much oxygen, this much iron, this much mercury, this much uranium, this much, go down the period table of elements, and it actually, you have each fingerprint. So you get down to people looking at stars, looking at strontium, and like, didn't even know that was an element. We're really looking comets just dissolved in the atmosphere, that kind of thing. So, but the second part is, how fast is the whole thing moving? Is it going towards me, or is it going away from me? Now there's one piece missing. Doppler shift only tells me if it's coming towards me or away from me. If it's moving along, I don't hear that, right? The pitch doesn't change. I don't get blue shift or red shift. So this radial component, I can see that. That tangential component, I don't get that from the Doppler shift. So I'm getting a velocity, but it's sort of like the lower limit of the velocity. The thing could actually be going a little faster because this part I'm missing. But I do get some information whether or not it's moving away from me or it's moving towards me. So I'm getting two pieces of information, what it's made of and how fast it's going either towards me or away from me. So okay, you thought you could escape the whole class without a tiny bit of math in there, but this is a science class and I will sprinkle it in there. So this is how we express that. The velocity basically as a fraction of the speed of light. A lot of things in the universe go pretty darn fast, so we do it as a fraction of the speed of light, and that tells us the shift. So this is the wavelength that we observe, we see how much it has shifted, and this is the wavelength that as we would observe it in the laboratory, the one that we know where it should be at if it's this element. Okay, so shifted wavelength of the spectral line, the rest wavelength. So rest or laboratory, right? So that's the one that we just observed. And then anytime it's shifted, we can tell how much it is moving along the line of sight, like towards or away from us. Okay, Doppler effect causes light from the source moving away to be shifted to shorter wavelengths, to be shifted to longer wavelengths, change the velocity, both A and C above, both B and C above. So, 41, 42, 43. All of them right? Yeah. Goes to longer wavelengths. So, you observe two spectra, shown below, right? Spectrum A, spectrum B. This side is blue, that side is red. Which of the following statements describes the sources of light produced the two spectra we're moving? Source A is moving faster than source B. Source B is moving faster than source A. Both sources are moving at the same speed. It is impossible to tell looking at these spectra. You observe two spectra, shown below, that are redshifted relative to that stationary source of light. Which of the following statements describes the sources of light that produce the two spectra we're moving? So, what do we know? They're redshifted, and both are moving. Photon 1, photon 2, photon 3. Let's see them. I'm seeing majority B with lots of minority opinions, so I'm going to walk around, turn to your neighbor, even if the two of you agree, and convince them why your answer is right. You've got about 90 seconds.
Yeah, but like they're the same, just one's this way and one's that way. So like can't really tell if they're faster.
One, two, three. Let's see. I've got A and B, basically majority B. All right, let's look at this. Two spectra shown below that are redshifted. They're both moving, they both move towards the red, right? Both patterns have moved to the red. Which one of these two has moved to the red the most? Is the next question. A or B? B, right? So this pattern, you can see that it's moved all the way over here. So source B is moving faster than source A. We already know that they're both redshifted, right? So this is where, this is one of those word problems. We have to look very carefully if one of them. Oh, question, yes?
I said B, but I'm just like wondering, because I could see where it would be like hard to tell, because how do you know where they started? Like,
Right. So what's my rest? So if I say something with this, for example, one of them is at rest and one of them is redshifted, which one of them is redshifted?
Right,
Then A is my relative point and B is my redshifted point.
right.
I give you a couple of them. One of them is at rest, one of them is blue shifted, and two of them are red shifted. Can you order them, right? So one of them, right, that might be easier to show. Do I have?
I was just thinking, because if they were, I mean, they started from the same place, but if they're both moving towards, it doesn't technically say. So, A started off, you know, farther away, could be moving at the same speed as B.
It doesn't matter how far away they are. It's just the speed that we're seeing along the line of sight. If they're moving together at the same speed, we should see the same shift. If this one's moving faster towards you, they're going toward, my fingers are now going towards you, they're going away from me, so that makes, all right, let's do it like this, that makes more sense. Right, so the sources are moving away from me. If they move at the same speed, doesn't matter how far away they are, if they move at the same speed, the shift is the same.
Okay.
And so this one's shift is bigger, this one's shift is bigger, so it's moving faster. It
Okay.
could be here, it could be just overtaking it.
Okay.
All right, thanks for being here, that's great. Okay, a bright star is moving towards Earth. If you were looking at the spectrum of this star, what would it look like? It's moving towards Earth. An absorption spectrum is redshifted relative to a moving star. An emission spectrum that's redshifted relative to a moving star. A continuous spectrum that is blue shifted. An absorption spectrum that is blue shifted. A continuous spectrum that is redshifted relative to an unmoving star. All right, which one of these do you think is the most likely if we're looking at a star with an atmosphere that's moving towards Earth? 41, that's a hard one. 2, 3. So, you'll go, nope, nope, nope. Has to be one of those two. Is it a continuous spectrum or is it an absorption spectrum? Well, it has an atmosphere, so an absorption spectrum would tell us if it has an atmosphere, a cloud around, right, an atmosphere around the star, you see absorption features, so an absorption spectrum, and it's blue shifted relative to an unmoving star. Well done. Okay. Wait, we got most. Continuous spectrum would also work because it's a hot ball, which maybe doesn't have an atmosphere. Not every star has an atmosphere, a noticeable atmosphere. So C or D would have worked. D I like a little better because most stars do have an atmosphere. If you observe an H alpha line, rest frame wavelength, the laboratory wavelength of 656.3 nanometers from a certain star at 656.0, is the star moving towards or away from us? Is it A, away, towards, cannot tell, moving sideways? 1, 2, and 3. I've got a mix of A and B. All right, so I'm going to walk around again, turn to your neighbor, even if the two of you agree, and convince them why your answer is right. You got it back on the side. All right, and we still have A and B as the two answers. Okay, so the rest frame wavelength is 656.3, right? So it's longer than 656.0. That is a shorter wavelength. You observe it at a slightly lower wavelength. Just a tiny tad, right? Just 0.3. Yeah. See people do this, and I'm like, yep, figure out which one is the rest frame wavelength, figure out which one's like, okay, I should see it here, where do I see it relevant to where that is, right? So we say rest wavelength, we see like rest. This table was at rest. It wasn't moving with respect to me. This was my laboratory wavelength. Okay, this is my laboratory wavelength. This is shorter than that. Shorter means bluer. It's blue shifted. It's coming towards me. Just a little bit. All right. So yes, we can actually tell if stars are coming towards us or away from us. So we're actually tracking, where stars are going in our Milky Way. So what we can learn by analyzing starlight, so this is sort of our summary slide, we can get the star's temperature. So by just looking at the peak wavelength, just where the whole thing peaks, that gets us the temperature of that star. So the first thing that we found when we were taking spectra back in the 19th century is that not every star is like our sun. There's ones that are hotter, there's ones that are cooler. But they all have several thousand degrees to 10,000 degrees, but there's a whole range of those. And then secondly, the star's chemical composition. Where are those dips in it has an atmosphere? The spectral curve will align with the spectrum. So we can actually see what it is made of. And that's when people realized that shoot, I can't get her name. So there's a woman who actually writes her PhD thesis, one of the first women to do that, and goes, I think the sun is made of mostly hydrogen. I think most stars are actually made out of hydrogen. And yes, turns out those are the dominant dips in the spectrum. That's actually what most stars are made of. And we can see what a star's motion is. So if we look at any given thing in the universe, we can learn these three things almost immediately. Its temperature, what it's made of, and how fast it's going. Not bad for just getting the little pinprick and running it through a spectrograph. So spectroscopy became this like little superpower for astronomy. As soon as we got enough light, our telescopes got big enough to put the light through a spectrograph and then take a picture of it, it would get us like, here's the fingerprint. This is what it's made of. It's going this fast relative to you, and it's got this temperature. So you start learning loads of things about the stars that we can see or the stars we can observe, and later we also learned about galaxies as well. So I have a group work about Doppler shift. So yes, you kind of, if you have a feeling like, wow, you just sped run us through light, yes, I did, because this is how we learn everything else, right? So I wanted you all to get the concepts of light so that we will just continuously use this for the rest of the semester. If I talk about, oh, galaxies are redshifted, you go like, what was it in week 3? Oh, right, I'll go back and, oh yes, redshifted, moving away from us. Okay, got it. So I try to switch it up so that I don't run out of paper on this side every time. This is the rules. You team up with a couple of people. I only have to get the group work from the group, right? So put all your names on there. Move it along. If you want to keep one, that's perfectly fine. But team up because I want more than one name on each group. You may notice that we don't have we only have a black and white photocopier in our department. No matter, we've got features that we can use. So this is sort of what it looked like during this Q&A. You guys got leftovers. I think I've run out on this side.
Oh.
Walk around, here for questions. Anybody needs an extra? Collaborate on it.
lock the doors out here.
Yeah, that's fine.
Running away. I'm assuming not here.
I realize the age, agency didn't quite come through, so.
Kind of scared here.
Anybody else down the road, any questions about this? I always pass this class, because that can be temperamental, so I will, put an extra, bit of extra time. This is the first time it worked without any issues or electrical pneumatic oil, so. So, it gives you three options, right? One of them is blue, one of them is red, and one of them is at rest. So, the one at rest has to be in the middle between the one that's blue shifted and red shifted. And that gives you relatively, like, okay, this one's in the, is at rest, these two, this one must be the blue shifted, and this one must be the red shifted. We often look at blobs of stars, loads of them, and so we see lots of them moving towards and away from us. So it's like, which one is roughly in the middle? So we do this exercise. I'm nearly done. Walk around, you can ask some questions, this is why we are, something's not clear. Yes. If there's two of your football names on there, that's what I'm gonna say, like, that's, you can keep it, I just make a few extra. So let's have a look at them, right? So, A and C almost look the same. And if I look at my things, like C is actually a little bit towards the blue, and A is a little towards the red. And then B is even redder than that. If I say one of them is blue shifted, one of them is red shifted, and that means that leaves one in the middle. That's the rest ring. The rest is at the left hand. So factory setting, I love this, factory setting, let's go with factory setting, I love this phrase. Yes, so A is the factory setting because C is blue shifted with respect to the factory setting. And so, and then B is red shifted with respect to the factory setting, because I gave you three options. I say three different options, if I say, okay, one of them is in the factory setting is a rest, I'm gonna start using that, because it's fun. And so, one of them is, let's say, different problem, right? So let's say, two of them are red shifted, and one of them is at rest, the factory setting. That means we pick the bluest one, that's the factory setting, the other two are red shifted. Right, so often we end up with a bunch of these things, like, all right, where are they with respect to? And so you sort of start ordering them. So he is looking at, and doing this problem, A is the middle one, that's the factory setting, the rest. C is blue shifted just a little bit, and B is moving away, looking away from us. This is a lot to do in one go, right? I'm tooling you all up so that you can go and you understand what I'm talking about. Like, this is why we learned all of astronomy until about 2015. So all of it came from basically doing this better and better. I love factory setting. I love starting doing that. How are you doing? Everybody sort of done? Almost done? Fantastic. Okay. So the reason that I padded this a little bit is that I allow for accidents with this to, it takes us sometimes way longer to switch these out. One of them has electrocuted me on occasion, or Drew, so I'm just trying to avoid that. And so I had that a little bit. So we've now learned all three things that we've like. We've learned what we can learn from light, right? So if you get this little dots of light in the sky, you run it through a telescope, you run it through a spectrograph, it will tell you the temperature, it will tell you the composition, it will tell you the speed. Okay, there are many stars in the sky, let's get to it, right? So get all of them, and that's really what the 19th century was all about, trying to figure out what all the stars were made of. Yes?
Can you find motion without knowing where it's stationary?
So you've just accidentally stumbled on but you've hit on the one thing that is very tricky. We can do relative motion. We can think that we're stationary, but we're not. We're on a ball that's circling a sun, and that sun actually circles the center of our Milky Way. So everything is relative motion. This is relative motion with respect to us. And we'll see that pop up back and forth, especially all the way so keep this in mind for week 15 when I'm talking about the universe as a whole, but we'll actually see like, hey, that part of the sky is all blue shifted, that part of the sky is all red shifted. Is that part of the sky special? Are those two special parts? No, we're going in that direction. The sky isn't red and blue shifted. We're traveling in that direction. We can actually see. So, do we see our own speeds? Do we see our own Doppler shift? Do we see our own velocity, or do we see the other things' velocity? I have a minute, and so I'm gonna take it. There's a funny anecdote that I can do here, which is that when the very first exoplanets were found, the first one had a period of 6 months. And every time we hear a period of 6 months, that's like, well, that's the period that our Earth does, right? It has a 6 months, for 6 months of the year it moves towards you, and 6 months of the year it moves away from you. So if you see something that has a wobble of 6 months, you go like, are you sure that's the star that you're looking at that's wobbling, or is it us? And it turns out it was us, and the whole exoplanet went away. And so the team that did that did the sanity check, had already put the announcement in, so they're going up in front of all their colleagues and go, we did the sanity check, the planet went away. The next team that came up on the stage went, we also, inspired by their find, went to look for these. We did find that the planet, it doesn't have a 6 month period, it has like a 4-day period. So that's definitely not our speeds, it's the exoplanet, it's the old planet. That was the first discovery of that. Both teams got it at standing ovation. You check your work, right? You check if this is like, did I take out the Earth's motion okay? And the answer is often not quite, or you forgot about this little thing, so yeah, you do it properly. We measure the relative motion, not the absolute one. There is no absolute point of rest. Everything moves in the universe, and everything moves relative to each other. So we always see Doppler shifts, one way or another. All right, this is our main tool. We got the two main tools. We got spectroscopy, we got black body radiation. These are the two things that will keep popping up. These are the two physical things that we keep using. This is the two pieces of physics you need to understand the universe. Except for one more thing, which is gravity, which is what we'll talk about next week. All right, fantastic. Thank you all for coming. Thank you all for doing spectroscopy with me. Please put the slides on the technical station and put your group works there as well. Sorry, that's the easiest way to collect everything. So, thank you. If you have questions, come to me after class, absolutely. I'm trying to set up a office hours, but I don't have an office. Oh, I made a whole bunch extra just in case, I don't know, it was a company like office. pass on it because I want to get it right. No, this is absolutely, let's get it right now so that we get it right throughout the semester.
Yes.
This is what we use the whole time, so that's why I'm like, all right, we're just gonna spend a little bit on gravity, scales, and light. Those are the three big concepts. And then
Yes.
that's it. That's all the concepts we need for a semester of physics for the whole thing.
Thank you so much.
Have a good weekend, and I'll see you on Tuesday.